And now we go on question 4 of the third midterm, a Bode plots question. A transfer function is given by a ratio of two polynomials, these two polynomials. The Bode amplitude plot has a value of 0 decibels at omega 1000 radians per second. Part A, determine the value of the constant k, this constant k here. Part B, plot on a semi-log paper and using a ruler to trace lines the Bode asymptotic plot for amplitude in decibels. Part C, do the same for phases in degrees. Part D we'll read later when we work on it. Let's begin. Allow me to copy the transfer function over to the next slide. And the first thing I'm going to do is find what are the zeros and the poles. What are the roots of the numerator and the denominator? Finding out the roots of the numerator is quite easy. We can factor out a square like so and realize that there is a double 0 and 0 and that there is another 0, a simple one, on the right hand side of the complex plane. We'll deal with that later. The roots of the denominator are a perfect work for the HP50G. We write the coefficients of that polynomial in a vector, issue the command polynomial roots, and get 4 roots. Those 4 roots, 2 real ones in -100, -900, and 2 complex conjugate ones. Those 2 represent a quadratic term in the denominator. That quadratic term has an undamped frequency and a damping factor. To find the undamped frequency is easy. We just have to take the absolute value of either of the 2 complex conjugate roots, like so. That is the undamped frequency, 12,500 radians per second. And if you are not sure why I'm doing that, I invite you to review another video in this series in the same channel called The Final Tutorial on Bode Plots. And to find the damping factor, allow me to swap that. All I do is take the cosine of the argument of that eigenvalue, either of them, the absolute value. Argument 101 degrees, and now we take the cosine, and the absolute value is the damping factor 0.2. Now we know what the quadratic term of the denominator looks like. It looks something like this: a squared plus 2 times 0.2, 12,500 plus 12,500 squared. The numerator is what it is, and the denominator has those 4 roots. We are ready. We are ready. Let's do the plot of amplitude. We trace a line, a horizontal axis, where we will do the plot without any scale in mind. I will mark the different corner frequencies approximately equidistant, 100 radians per second, and then 500. You say, wait a minute, -500? No. As we have seen in another video in the series called Addendum to the tutorial on Bode plots, a 0 on the right-hand side of the complex plane behaves in amplitude exactly as the corresponding 0 on the left-hand side. So, for the purpose of amplitude, this could have been a term s plus 500, ergo 500, and then 900, and then 1000. You say, wait a minute, there is no corner frequency at 1000. No, there isn't, but at 1000, we know what is the value in decibels of this Bode plot. Remember, 0 decibels is one of the pieces of data. And the corner frequency, 12,500 radians per second. And we begin. We enter from the left according to this double 0 at 0 with a slope of positive 40 decibels per decade up to the first corner, where this pole reduces the frequency by 20 decibels per decade. And then here is another 0, this one, that increases the slope by 20 decibels per decade to 40. And now a pole, a simple pole at 900, that reduces the frequency down to 20 until the final corner frequency, the undamped frequency of the quadratic term, that reduces the slope by 40 decibels per decade down to negative decibels per decade. And that is the asymptotic plot for decibels. You say, wait a minute, but I have only the corner frequencies and the slopes. What about values? Well, one thing we know is the value of this approximation here at 1 kiloradians per second. It was what? 0 decibels it's given. And with that and the slopes, we can find all the others. With this, 1K, 12.5K, and that slope and 0 decibels, we can compute that the value here is 21.94 decibels, and we can do the same backwards and find that the value here is negative 0.92 decibels, etc., negative 1113, and negative 2511 decibels. Now we have completely determined the Bode plots. We are almost ready to plot it on semi-long paper. But before doing that, let me determine what is the distance between the two extreme corners in decades. There are 2.1 decades between the first corner and the last one. That allows me to center my plot in the semi-long paper. And vertically the distance is 47 in decibels. That allows me also to center my plot in the paper vertically to make it look good. To find K, we realize that at the lowest corner, the value is negative 2511 decibels, but that value can be computed also as 20 times the logarithm of K times 500 divided by 100, 900, and 12,500 squared. In other words, at a very low frequency, at a frequency of 0, that is the value of the amplitude of this one. And of course, we have to add what is the contribution of the double zero at 0. That is this number of decades away from 1. Logarithm of 100 over 1 multiplied by this slope 40. That is the contribution of that double zero and 0. That added has to be the value we know. We can solve for their K and find it is 156,168. And that is the answer to part A. And you say, wait a minute. What kind of a fancy piece of software you used to find K out of that equation so quickly? No fancy software, just the fancy HB50G. Observe, that is the equation. Let me expand that a little bit and write these as 20 times log K plus 20 times log the rest. So we have a linear equation in log K. Let me call log K X, that is my unknown, and we can enter that in the calculator and solve for X, which is log K, and find the antilog to find K. See? Piece of cake. Let me do just that. All my students have access to the calculator, and all the viewers of this channel have access to the free emulator for PC. We type that equation, write negative 25.11 decibels, but with integers. That is equal to 20 times X. X, remember, is the logarithm of K, the unknown we're trying to find. The rest of the equation is same old, same old. Once we have it ready, we can use a symbolic solver to find for X. But X will come as an equation, X equal to something. Let's eliminate the left-hand side of that. Object to pieces, delete and delete, swap and delete, and that we want the numeric value. Give me the numeric value of that. That is log of k. Anti-log of that, 10 to the, that is 156,000 and some change. Exactly the value that I had shown you before. Now, this is the exact amplitude plot for that function. And you're saying, wait a minute, who is whom? Well, this is 10,000 radians per second here. This is 1,000, exactly where it is 0, right? Right there. And this is 101 and 0.1. What is with that peak, that spike, that hump the curve has there? Well, you remember that at 12.5 kiloradians per second, there was a double pole there, a complex conjugate parapulse, but it had a damping factor that was tiny. It was 0.2. That's why that has that big hump, that big spike. For the phase, we remember that a 0 on the right-hand side of the complex plane is equivalent only for phase to this, a double 0 at 0 and a one simple pole on the left-hand side with the same value, s plus 500. Only for phase, this transfer function at the bottom is equivalent to the one on the top. This is the one we will work with. Let me copy that on to the next page. If you don't remember that, please watch again the addendum to the tutorial on Bode plots. This one, the terms on the top, contribute with 360 degrees across all the frequencies. And this one with two corners, one at 10, negative 45 degrees per decade slope, and one at 1,000 with plus 45 degrees per decade slope. This one 50 and 5,000. This one 90 and 9,000. What about this one? Well, we have to find two frequencies, one that is 0.2 decades below 12,500, this one, and one that is 0.2 decades above 12,500, which is 19.8 kiloradians per second. What is the slope contribution of this one? It's 90 degrees divided by 0.2. That is negative 450 degrees per decade, the first one, and positive 450 degrees per decade, the second. And if you don't remember this, please go and watch the final tutorial on Bode plots in this series. Same thing, the graphic, and approximately equidistance, because this is not an up-to-scale graphic. We mark all the corner frequencies from left to right, 10, 50, 90, 1 kilo, 5 kilos, 7.9 kilos, 9 kilos, and 19.8 kilos. And we have here the contributions of slope for each one of them. On the left, we know we begin with 360 because of the 4 zeros at 0. 360. We hit these 10 radians per second, and the contribution is a slope of negative 45 degrees per decade. Fine. And at 50, another 45 degrees per decade. We cave in. With the first two values, we have the value of 360 and 10. We have the slope between 10 and 50, and there is a drop that gives me the value here, 328.6 degrees. The same thing between 50 and 90 and the slope. We know the value here. We can compute that this value is 305 with 6 degrees. And I keep doing that, adding each slope and computing the value on the corner for each one of them. Slowly or quickly, until we arrive at the very end, that is negative 89.6 degrees. And that is the phase plot for that transfer function. if you plot it like this in the exam, if you drew it like this, where you indicated every slope and the value of every corner like so, you have that graphic correct. But let's see what it really looks like. The horizontal range for the plot between 10 radians per second and 19.8 kiloradians per second is 3.3 decades. We gotta remember that to center the plot on the graphic paper. And the vertical range goes from 360 at the top to -90 at the bottom. That is 450 degrees that we need to allocate on the vertical axis of the plot. This is the graphic. Of course, this is the exact one. That is pretty much like the one we found in the previous slide. Now, part D. Part D was at the frequency of 12,500 radians per second. Find both the approximate value given by the asymptotic Bode plots and the exact value computed from the actual function of transference and compare them. The approximate value at that frequency from the graphics we have is, this one is already in the graphic, is 21.94 decibels. Computing this one is quite easy, 0.3 degrees, and we evaluate the actual transfer function at the frequency 12,500 RPM, and this is what we get. Now, the error is computed in percent with respect to the maximum range between corner frequencies on the corresponding axis, on the vertical axis, right? With respect to the vertical span between corners. If you got those four values correct, you have the answer correct already. But much better if you wrote it like this. The penalty was minimal for not computing the percent correctly. The difference divided by the range. Difference divided by the range. And that is all for this question. Question 4. The heavy weight of the questions in this exam. Thank you very much.